Hi there. My name is Dwayne Habecker. I'm from the Merced County Office of Education, and the purpose of this video is for us to begin the process of digging into CRA, the CRA approach, particularly as it pertains to middle school. Although the CRA approach works for kinder all the way through 12th grade, this video is really going to focus on first an overview of what is CRA instructional approach, and then I'm going to give some specific examples for how it connects to the middle school curriculum. Now, let's keep it real here. I'm going to manage our expectations a little bit. Learning how to do CRA is a little bit like learning how to play chess. About a year or so ago, my son, he was 14 at the time, asked me to teach him how to play chess, which I'm totally stoked to do, happy to teach him, so I taught him. And to be honest, it took about 15 minutes to teach him how to play chess. And we began playing our first game after about a 15-minute introduction. Now, he sucked after 15 minutes of instruction, but he was still able to play the game. That's what the CRA instructional approach is. It takes us about 15 minutes to learn about, but then it takes the rest of our instructional career to get really proficient at it. This video is going to be a little bit longer than 15 minutes, but it's going to be a whole lot less long than the rest of your career. So let's just go. Oh gosh, I don't know. That was the dumbest thing. So let's get started. Okay, so I'm going to start with this idea of where we're coming from. So the MCOE math team, we have a vision for how students learn best. It comes straight out of the National Council of Teachers of Mathematics. And really what we want to see is we want to see every student be enthused about mathematics. We want them to see the value and the beauty of mathematics. And here's the kicker: we want every student to be empowered by the opportunities that mathematics affords. So if that's what we want, how do we get there? Well, we get there through what we call the mathematics hierarchy of needs. The mathematics hierarchy of needs is a step-by-step roadmap that doesn't have to necessarily work in sequence. They can happen all at the same time. But it's a multi-layered approach for how do we eventually get to the top, which is math literacy. We begin with material needs. Then we work our way to mindset and culture. Then we build our way to student-centered instruction. Then we use equitable assessment. And then when we do all of these things, we know the result is confident problem posers and problem solvers. Basically, we have students who are mathematically literate. Now, where does this come from? This comes straight out of Maslow's hierarchy of needs. And then we mathematized each of those layers. So Maslow's physiological needs becomes material needs. Safety and security becomes mindset and culture. Love and belonging becomes student-centered instruction. Self-esteem becomes equitable assessment. And then where Maslow says we've reached our highest point when we become self-actualized, we call that mathematically literate. I encourage you to pause the video here so that you can compare and contrast these two hierarchies, Maslow's and then the math hierarchy of needs. What we're going to be doing this year for Atwater Elementary School District is we're going to be focusing on the CRA approach. And the CRA approach lives in that mindset and culture layer that says all students can learn, and we're going to normalize mistakes as a normal, necessary process for students to develop conceptual understanding. The neat thing about mindset and culture is it also requires us as the instructors to kind of develop some new teacher content knowledge, because quite frankly, it is very unlikely any of us were taught mathematics with a conceptual point of view, it is very unlikely we were taught mathematics through the lens of CRA. So we're going to have to do some relearning of mathematics, likely, so that we can incorporate the philosophy and the mentality of CRA into the mathematics that we already know. It's really kind of cool. So let's get into some specifics. Some basic research we've known for a long time. Two resources, one U cubed, and then the other one is the IES. I can't remember what IES stands for, but the WWC stands for the What Works Clearinghouse. I think it's Instruction Education Services. I don't know what IES. I can't remember. But these are two sources of research and information that both make it abundantly clear when we include those visual representations, that improves student performance. It improves student outcomes. We've just had decades worth of information saying so, and yet quite often our curriculum, our textbooks, the way we were taught ourselves is really heavy on the abstract and on numbers and on algorithms without the very thing that we know we need in order to increase performance, which is those visual representations. So everything we're talking about is grounded in decades worth of research. So what does CRA stand for? So CRA stands for Concrete Representational Abstract. And basically what that means is that C, concrete, R stands for representation, A, abstract. Collectively speaking, it's a highly effective teaching progression that is particularly effective with developing conceptual understanding, and it's that conceptual understanding that leads to procedural fluency. CRA is also especially effective with our generally hard to teach students, particularly our students who are learning English as an additional language and students who come to us with learning disabilities. CRA is effective K through 12 and across all math topics. C stands for concrete, where generally students are using manipulatives. And I understand Atwater Elementary School District is ensuring that all teachers have manipulatives and are fully equipped with the manipulatives they need. Please talk to your principal if you have not received your manipulatives yet. Once students are kind of done with their concrete phase, they then move into the pictorial representation phase. Although some countries call this CPA, in the United States it's most often called CRA, concrete representation and abstract. Other people call it concrete pictorial abstract. So that R is where students have graduated from the manipulative stage and they are no longer holding on to the concrete manipulatives. Rather, they're drawing pictures to represent the things that they formerly used to touch. And then the last stage is abstract. And abstract is where students are using numbers and symbols to represent the pictures that used to represent the manipulatives that they used to touch back in the day. Now, the thing I don't want to let you lead you into this misunderstanding is CRA does not happen in sequence. They all happen simultaneously. We may begin with some concrete stuff only, but when many students move to the pictorial phase, we are still making the concrete manipulatives available so that students can move back and forth between the two and then ultimately between all three stages of development. So CRA doesn't happen in sequence, it happens simultaneously. Another way to think of CRA and it happening simultaneously versus sequentially is I want you to think of time, this x-axis, as time. Time is ticking, and time might be days, weeks, months, or years. And I want us to think about, okay, we're teaching a concept. And initially, we might teach that concept through concrete. We've pulled out the manipulatives. Everybody is building, using those manipulatives to understand the conceptual understanding that we want to get them to. And eventually, what's going to happen, time will be going on, and a student is going to come up to you and say, really? Do I have to keep building with these cubes or these base 10 blocks? And you say as the teacher, I don't know, do you have something in mind? And the student will say, well, yeah, instead of me using the manipulatives, can I just draw a picture of them? And you say, wow, that's pretty lazy. Go ahead. And now the student is pushed into the R phase, representation, while most of your other students are in the C phase. So you're teaching a lesson and your class is now in two unequal groups. Some students are learning that lesson through the concrete. Other students are learning that same lesson, through the representational phase. And then eventually some student is going to come up to you and say, really? Do I have to keep drawing these pictures? And you say, well, do you have a suggestion? And the student will say, well, yeah, instead of me drawing all these pictures, can I just use numbers? Instead of drawing 8 cubes, can I just write the number 8? And you say, wow, that seems pretty lazy, but go ahead. And now all of a sudden, you're teaching a lesson, and your students are now in 3 unequal groups. Some students have pushed all the way into the abstract phase with numbers and symbols. Some students are still in the pictorial phase, drawing pictures of and the concrete, which some students are still in that concrete phase. So you have 3 unequal groups. The key thing is, as time is ticking, each lesson I'm teaching, I'm only teaching one lesson. It's just that the students are self-differentiating into one of these 3 stages of development: concrete, pictorial representation, or abstract. Eventually, students are going to always be seeking out the phase of development that is most effective and most efficient for them. And so those concrete kids are eventually going to wean themselves of the concrete, and you're going to now have just 2 groups, the R and the A. Lastly, those R students are going to wean themselves of the pictures, and they will graduate just to the same abstract. And we call this the arc of development. Over time, you start with probably a single phase of development, but then their students differentiate automatically as they are able to. And then eventually you will end with that whole class being firmly in the abstract phase. Now, this timeline can be days, weeks, months, even years. It depends on the topic that you're teaching. Some lessons, some topics might begin the week on Monday firmly in the concrete, but within a day or 2, students are already in the abstract. At the middle school level, an example of this is adding negative numbers. It's pretty quick. This arc of development is a pretty quick timeline with adding integers, generally 2 or 3 days as you move from the concrete all the way to the abstract. Other topics, algebraic equations, might take weeks. One arc of development, long division, takes about 3 years. It begins in the concrete phase in 4th grade, and it doesn't end in the abstract, fully in the abstract, until 6th grade. So that's another connection to middle school. 6th grade long division, we will get to the abstract. However, we as 6th grade teachers may have to teach our lesson fully cognizant of the fact that some of our students are still in the concrete phase, some are still in the pictorial phase, some are still in the abstract phase. And our goal for long division in 6th grade is to get students firmly into the A, that abstract phase of development. So why do we have to do this? Why can't we just go straight to that A and say, hey folks, this is how it's done. Let me show you how to do it. Well, here's why. CRA allows us as the teacher and the students to focus on building conceptual understanding rather than just that algorithmic, memorize the algorithm and we don't need to know why it works. Just jump straight to that algorithm. Not to say that that's what you all do. This is life. I mean, this is how we generally, math has used to be generally taught, by jumping straight to that abstract. So CRA gives us the space for students to build that conceptual understanding. And folks, it's the conceptual understanding that forms the foundation for procedural fluency. This procedural fluency, this ability to do the algorithm, is only meaningfully learned when it's built upon this wonderful foundation of conceptual understanding. So CRA gives us the conceptual understanding, which then leads to the algorithm, the procedural fluency that we want. And this happens over time. That's the arc of development that we're talking about. Over time, students become skillful in using those procedures flexibly as they are solving contextual and mathematical problems. So it's this over time. There's our arc of development that we are talking about. Folks, I forgot to include, but this comes straight out of NCTM's language, their documentation. So this is not the Gospel of Dwayne. This is not the Gospel of Merced County Office of Education Math Team. This comes straight out of NCTM. So far we've talked mostly about CRA, concrete, pictorial representations, and abstracts. And the key thing is they feed on each other, and really it's not a sequence of events. It's all happening simultaneously, and students, even when they are at the abstract phase, they may go backwards or move over to the concrete or the pictorial. I shouldn't say backwards. They should just freely be allowed to move through and amongst these representations as needed, as the story problem requires, as the content, as just how they're feeling that particular day. Now, the more representations we provide for the students to go, the more connections their brains are able to make. We have two additional representations, contextual and verbal, that we also want students to be able to flow through and amongst, giving us a whole ton of connections. And we have tons of evidence that says when students are able to compare and contrast between representations, that increases student learning. And this ability to compare and contrast only happens, well, I should say it easily happens in the CRA approach to instruction. These extra little loops say that we can even connect one pictorial representation to another pictorial representation, or we can connect a concrete model, base 10 blocks, to another concrete model, let's say the chip model. So base 10 blocks compared to chip model, concrete to concrete. So we've just got tons and tons of connections connecting these things. Now, another way to say concrete is to say build it. Pictorial says draw it. Or we say write it in numbers. Now, what is contextual and verbal? Well, contextual is, tell me a story that connects to what you've built or drawn or wrote in numbers. And then verbal is to talk about the problem, to talk about the connections you see between these things. Now, why do we want to have all of this confusion and all these representations and all these lines and everything? Well, the research is clear from Silver, but then also Dr. Marzano comes up with some similar research. It's clear, the research is clear, that strategies that engage students in this comparative thinking, this idea of comparing and contrasting between multiple representations, those strategies have the greatest effect on student achievement, leading to an average percentile gain of 45 points. So why do we want all of this? Why do we want CRA? Because the research is clear. When we measure student progress, students gain more when they've had access to a CRA approach to instruction. Now, because CRA is like chess, it took 15 minutes. I'm kind of done telling you what CRA is. But now it's going to take the rest of our instructional careers for us to get good at it. How do we apply? Now that I know what CRA is, how do I apply it to my unique situation in my curriculum, with my books, my students, with my level of understanding of mathematics? And so that's where, hopefully, this is going to be the beginning of a long journey where I get to keep coming back to your school, assuming we get subs, and we get to do math together and figure out how do we apply that CRA approach to each of your individual content areas. So we're going to do a couple of examples just really quick because I don't want to turn this into a terribly long video. So let's do some examples and long division. So CRA with long division. So this is a 6th grade example. And why is this important? Well, long division is one of the 2 required fluencies in 6th grade. And quite frankly, students have been learning long division for decades since 4th grade, right? And we've always historically started long division in 4th grade. And by 6th and 7th grade, students still struggle with that long division algorithm. Why? It's because they were never taught through the CRA approach. So the CRA approach with long division, very briefly, we're gonna do this training in person, but the idea is we model, in this case, let's model 579 divided by 4. And this is what 579 looks like. There's my 500 right here, there's my 70, and there's my 9, so 579. And then we do stuff with it. Now, what does that stuff end up looking like? Well, in the representational phase, it ends up looking like this. And through this pictorial representation, I can see that the answer is 144 with a remainder of 3. When I do 579 divided by 4, I get 144 remainder 3. What does that look like as the abstract? Well, here it is. It's not exactly the standard algorithm, but the Common Core doesn't say 6th grade long division has to be the standard algorithm that you were taught. It just has to be a standard algorithm. And here is a wonderful standard algorithm that indeed even works as we move into the decimals of 7th and 8th grade. In fact, let's do a quick example of what this would look like. And so here is our long division in concrete form. So the idea of 579 divided by 4 is this divide by 4 means I need to take my 579 and group it into groups of 4. So there is one group of 4 in my hundreds column, and I have a remainder of 1. So what am I going to do with this remainder of 1? I'm going to cache this 1, this big, in for 10 littles. So this 1 big is equal to 10 in the next column over. So I'm going to cache this big in, and I now have a whole ton of 10s. And now, because I'm dividing by 4, I want to create groups of 4. So there's a group of 4. There's a group of 4. There's a group of 4. And I still have extra cubes left over. So here's another group of 4. So I've made 4 groups of 4. And again, I have 1 left over 10. So what am I going to do with that 1 left over 10? I'm going to cache it in for 10 ones. So I'm going to get 10 ones. So I'm going to cache this 10 in, and it's going to give me 10 ones. So now I have a whole ton of ones here. And again, I want to create groups of 4. Why am I creating groups of 4? Because I'm dividing by 4. So there's a group of 4, 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 and I have 3 remaining. So what is my answer? My answer is 100. I have 4 groups in the 10, so 40. I have 4 groups in the 1, so that's 144. And there's my remainder 3. And all of that happened concretely. It's pretty darn quick. Now, what is that going to look like pictorially speaking? Well, pictorially speaking, let's get so we're dividing by 4. So we're doing 579. And I'm going to build it right here. So here's my hundreds, here's my tens, and here's my ones. All right, and let's build it. So 1, 2, 3, 4, 5. There's my 500. 1, 2, 3, 4, 5, 6, 7. There's my 70. And 1, 2, 3, 4, 5, 6, 7, 8, 9. There is my 579. There we go. Now, because I'm dividing by 4 right here, I need to separate these into groups of 4. So here's a group of 4. Uh-oh, I have this extra guy left over. So what am I going to do? Well, I'm just going to cache him in for 10 tens. So 10 tens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this 100 got cashed in for 10 tens. All right, so now I'm going to create groups of 4. So there's a group of 4, there's a group of 4, there's a group of 4, there's a group of 4. Uh-oh, I have 1 10 left over. What am I going to do with that 10? I'm going to cache him in for 10 ones. So I'm going to cache him in for 10 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now, because I'm dividing by 4, I'm going to find my groups of 4. There's a group of 4. There's a group of 4. 4, 4, and I have no more. I don't have enough to make a group of 4, so I'm done. And I can now see my final answer. My final answer is I made 1 group in the hundreds column. I made 4 groups in the tens column. And I made 4 groups in the ones column. And I have these 3 little guys left over. So my answer is 144 remainder 3. Now, how does this connect to that long division algorithm right here? Well, it's really stinking beautiful. Check this out. So in the hundreds column, I was able to make 1 group. So in the hundreds column, I was able to make 1 group. 1 group. I used up 4 hundreds, and I had 100 left over. Now, when I cached that 100 in, it gave me 10 tens in addition to the 7 that were already there. So this 100 gives me 17 tens. So I now have 17 tens, and that's what it looks like right here. And now I made 4 groups. I used up 16, and I had 1 left over. So I created my 4 groups. I used up 16, 4 groups. I used up 16, and I had the 1 left over, and that's right here. Then I cached him in for 10 ones, and so that gave me 19 ones, as indicated right here. I was able to make 4 groups, which used up 16 ones with my remainder of 3. And folks, there is my 144 with a remainder of 3. Pretty darn simple, pretty easy to do. It's a really nice system. Okay, so let's go back to our slide deck here. So there's just so much we can do. So I'm going to just really briefly give some brief overviews. We're not going to do any great details on the next ones. I want you to be thinking about these so that the next time we are all together, subs permitting, we can actually do the math together, because that's when it's fun. It's not quite as fun just watching a video. But let's push into some 6th, 7th, and 8th grade really quickly. CRA with ratios and proportions. Mastering proportional thinking is an essential part of having our students prepared for algebra in 9th grade. And really, quite frankly, it's essential for them to understand ratios and proportions is essential for them to understand the algebra of 7th and 8th grade as well, let alone the actual official algebra class. I get this from the final report on the National Mathematics Advisory Panel. It was published in 2008. And it's just this awesome document that says, hey folks, this is how we are. We have demonstrable evidence that says we're supposed to be teaching in a different way. CRA. So let's get going and doing this. So we've known for 13 years since this report came out that we should be teaching with a CRA approach, particularly in the middle schools. So I'm going to connect CRA directly to our Common Core standards. First, in this case, 6th and 7th grade. Here, straight from Ratios Proportions number 3, use ratios and rate reasoning to solve real world, there's your concrete, and mathematical problems by reasoning about tables of equivalent ratios, tape diagrams, and equations. So folks, this tape diagrams, these are pictorial representations. Equivalent ratios and equations is your abstract. So you've got your concrete, pictorial representation, and your abstract straight in your Common Core standards. 7th grade and 8th grade, by the way, we move from explicitly calling it concrete, pictorial, and abstract, CRA, and then we begin to call them tables, graphs, and equations. So tables is the middle school version of concrete. Graphs is the middle school version of pictorial representations. And then equations is the middle school version of the abstract. So CRA lives in middle school, but we begin to call it tables, graphs, and equations. All right. Although we still do concrete, pictorial representation, and abstract as well. So middle school is this wonderful, complicated amalgamation of the CRA of primarily K-5 and the tables, graphs, and equations, or tables, graphs, and formulas of 6 through 12. So let me give what I'm trying to say a pictorial representation. So while CRA is our initial approach, and that is indeed a K-12 thing, that really never goes away. We use CRA and will refer to CRA all the way through calculus. But what starts to happen at the middle school level is the concrete becomes tables, the pictorial representation becomes graphs, and the abstract becomes formulas, and that is largely a 6 through 12 only phenomenon. In fact, it's largely 6th through 9th grade. We probably drop a lot of this as we get into 10th, 11th, 12th grade. But really this tables, graphs, and formulas is a 6 through 12 phenomenon. And so what we're going to be doing for Atwater Elementary School District is we're going to be bouncing back and forth between CRA and TGF because of that unique nature of middle school. Let's dig into a simple example. This happens to be a 6th and a 7th grade example. A juice recipe calls for 5 cups of grape juice for every 2 cups of peach juice. How many cups of grape juice are needed for a batch that uses 8 cups of peach juice? Now, initially, when we ask students to draw this, they give us some sort of picture like this. At best, they might give us a bowl for the fruit juice and then some representation of our grape juice and our peach juice. All right. And so with CRA in mind, we're going to add a little bit of sophistication to that. Starting with the concrete. What does that look like? Ratios and proportions. What does that look like with concrete? Well, we begin with that phrase, 5 cups of grape for every 2 cups of peach, right there. And we're going to make a table. So there is our concrete, but we're also going to bridge it to actual concrete objects. So there's our 5 cups of grape juice going along with 2 cups of peach. And then we have 10. If we add another 5 cups of grape, means we have to add another 2 cups of peach. And now all of a sudden we have 10 cups of grape juice going with 4 cups of peach. Then we have another 5 and another 2, giving us 15 and 6. Then we have another 5 grape and 2 cups of peach, giving us a total of 20 cups of grape and 8 cups of peach, which allows us to now answer our question, how many cups of grape juice are needed for a batch that uses 8 cups of peach? Well, if you use 8 cups of peach, you must have 20 cups of grape. Now look at that. We have the pictorial representation that says so. 2 times 4 gives us 8. And then our 5 times 4 gives us 20. And oh my goodness, all of a sudden we're beginning to see a vertical relationship. 2 times 4 gives us 8. 5 times 4 gives us 20. So we're able to go back and forth from this concrete representation here to the table form, which is kind of playing both the abstract and the table version of the concrete simultaneously. Man, this is so stinking fun. We can then look at that. All of that's concrete, really. And we can equate it or relate it to the pictorial representation, where now students are merely drawing representations of the grape juice and the peach juice and connecting it to the tables right here as well. So we've got our concrete, we've got our pictorial, and the tables kind of bridging the gap from concrete to abstract as well, because if you look at the tables, it's just a bunch of numbers and symbols, isn't it? Moving into a 7th and an 8th grade example, I know it says 6th and 7th, but this is really pushing into the 8th grade. In the orchestra at Willard Middle School, a ratio of stringed instruments to non-stringed instruments is 5:3. There's 28 more stringed than non-stringed instruments in the orchestra. How many instruments are in the orchestra altogether? So we're going to begin with this answer sentence right here. There are blank instruments in the orchestra. We're going to begin the process of learning how to represent that problem, pictorially speaking. In this case, we are using a tape diagram and modeling with that tape diagram. It allows us to outsource our thinking onto the paper. Once we have outsourced our thinking of making sense of this context, and we've outsourced it to the paper, then we can refresh our brain and begin thinking about the second step, which is now let's start doing the calculations in order to arrive at that answer. I'm going to let you play with this problem right now rather than giving you the actual work and the answers, but play with this. So feel free to pause this video and use this pictorial representation to dig into this problem. 7th and 8th grade, we are firmly in, we've moved, we definitely need to get our students into that tables, graphs, and formula mentality of CRA. And we're going to be using the Frayer model to relate and connect the various relationships between the context, the formula, the table. We prefer to use the XKY table where that constant of proportionality is the middle column, and we do prefer to do it vertically like this as opposed to so much curriculum does it horizontally. We prefer to do it vertically simply because that X and the Y begin to relate to the coordinate pairs or coordinate pairs that then get graphed. So we like to do it that way. CRA can happen with integers. Neat thing about integers is that number line bridges both concrete and pictorial representation at the same time. So according to the research, whenever students are using a number line, they're really kind of got one foot in both lands of both territories, the concrete phase and the pictorial representation phase at the same time. We can use that number line and take advantage of that research that says the student's brain is now operating in two locations, concrete and pictorial representation, to make their brain work extra hard. And that productive struggle allows us to create a deeper understanding, increased neural networks, neural pathways. And so we can use the number line to represent addition, a variety of addition problems. Feel free to pause on any of these so that you can take that representation, the abstract representation, and connect it to the pictorial representation. So go ahead and pause on any one of these and really make sense of that connections between the abstract and the pictorial representation. We can do it with subtraction as well. Feel free to think about how does this definition of subtraction, which really makes use of, if this is the addition, definition of the addition, first change plus second change gives me the sum, then subtraction must be the sum minus the first change gives me the second change, which means I now have a pictorial representation for negative 13 minus 5. In the addition world, this negative 13 would have been the sum. That number right there is the first change. The first change is a 5. So what does that second change have to be if the first change is a 5 and our destination is negative 13? So what does that second change have to be? We can use CRA with expressions and equations, and there's just so much, particularly using that Frayer model to build those connections between the various stages of development. And starting with, this would be a 7th grade problem, probably 5 plus 3 times the quantity, 2x plus 1. In the concrete phase, we would say, well, that 5 is represented by 5 little algebra tiles. That 3 times the quantity 2x plus 1 is, there's a 2x plus 1, and we have 3 copies of 2x plus 1. And we can represent that pictorially like this, and that gives us the abstract like this. So our concrete leads straight to the abstract, which gives us 6 x's and 8 little unit squares. We could do this with more complicated problems involving subtraction. I'm going to go to solving equations with 7th and 8th grade, again using the algebra tiles and the balanced scale motif. There's a variety of motifs that we could use, but we're going to, a lot of research says that using the balanced scale and the weights, W-E-I-G-H-T-S, the weights motif is an effective technique for building that relationship between concrete, pictorial representation, and abstract. And folks, I'm gonna just say, as we wrap up, this video, very lengthy. And it's just a taste of an overview of what is CRA in general, why is it important to us, and then just a taste of what it might look like in some selected topics at 6th grade, 7th grade, and 8th grade, keeping in mind that we could do CRA. We can CRA-ify anything we teach at the middle school level, and that's what we're going to be spending a lot of our time doing, is figuring out how do we take our curriculum, CRA-ify it, and then use it with our students, and then watch the wonderful benefits happen. If you have any questions, feel free to contact me at any time. I'm going to have my contact information in this video thing. It's on the screen right here. I'll put it right here, and feel free to contact me at any time.